Okay, so today we're going to talk about a little bit of probability. So let's start by defining what probability is. If I said to you, what's the probability of getting heads when I flip a coin, you would all say what? 50% or fraction-wise, 1/2? Because you all have a basic understanding of what probability is, and that is the number of successes, number of successful outcomes, the number of successes over the total. So probability is the number of successes, that is what you want over the total number. Right? So if you roll a die, the probability of getting a 4 is 1/6, because there's 1 4, one face with a 4 on it, and there are 6 total faces. That's probability. That is different than odds. Odds are the number of successes over the number of failures. So these are different numbers. The answers are different. A lot of people use the two words interchangeably. Not in math class. In math class, they are different. So let's roll a die. This is just some basic background before we start doing the actual problems. What is the probability of getting a 6? And what are the odds of getting a 6? Okay? Well, tell me. Roll a die. What's the probability of getting a 6? 1/6. Because there are 6 numbers altogether, 6 totals, and one of them is a 6. So what are the odds of getting a 6? 1 to 5, that's right. And odds are usually written sideways, but if you write it as a fraction, that's okay too. If you watch like the Kentucky Derby and stuff, you'll see odds and they're written sideways like this. Okay? All right. Well, let's get to it. Here we go. So in the beginning, we're going to study 3 or 4 basic kinds of probability. And the first kind is the most basic. You have a probability chart right here in front of you. Maggie and Elizabeth have taken a bag of M&Ms and they've counted out, sorted them by color. And for example, Maggie has figured out that 30%, 30% of her M&Ms are green. That means that if she reaches into the bag and grabs one M&M, the probability it will be green is 0.3. And so on with all of the other colors. And then Elizabeth has all of hers too. So question A. Oh, I answered that already. This is Elizabeth. If a candy is chosen from Elizabeth's bag, what is the probability it will be green? 0.2. And you can answer that as a decimal, as a percent, or as a fraction. The only thing is, if you answer it as a fraction, it has to be reduced, okay? I would just say 0.2, since that's what I've got right here in my chart, but that's 0.8%. Now, if the candy is chosen from Maggie's bag, what's the probability that it will not be yellow? What? 80%, 0.8. Why is it 0.8? Because the yellows are 0.2, and won't everything else then be 0.8? If a candy is chosen from each bag, what is the probability that they will both be red? So in other words, we're going to get red and red. And we talked about a couple days ago that when you do this and this, that's going to be a multiplication. We're going to multiply. So what's the probability that Maggie will be red? Maggie red is 0.2. What's the probability that Elizabeth will be red? 0.3. Now, be real careful. Use your calculator if you need help. When you multiply these together, you do not get 0.6. You get 0.06. So the probability is 0.06. All right. All right, if a candy is chosen from each bag, what is the probability that neither will be brown? So no brown from Maggie. What's Maggie's not brown? Maggie, not brown, is not 0.6. 0.8. Kids, I can't tell. Like usual, you're just kind of sitting there. If 20% of Maggie's M&Ms are brown, what percent isn't brown? 80%, because the total is 100%, right? All right, what about Elizabeth, not brown? What's Elizabeth's not brown? 0.9? Now we want not brown and not brown. And whenever it's an and, we are going to multiply. So the answer to the question is 0.72. So there's a 72% chance that if you reach into each bag and grab an M&M, you won't get any browns. If a candy is chosen from each bag, what is the probability that the first one will be green and the second one will be blue? So green and blue. So we're gonna reach into the first bag, which is Maggie. We reach in there. What's the probability we get a green one? 0.3. And we reach into Elizabeth's and we want a blue one. So that is 0.2. And we are doing green and blue, so we're going to multiply those and we get a 0.06 or 6% probability. Now, read question F. What is different about question F? One will be blue and one will be green. So could the first one be blue and the second one green? Would that be okay? But is that the way it has to be? Or we could get the first one green and the second one blue. Do you see that in this problem? That it could go either way. And I'd have one green and one blue, right? So, Maggie blue is 0.1 times Elizabeth green, which is 0.2. 0.02. So, blue and green is 2%. Or we could get Maggie green, which is 0.3. And Elizabeth blue, which is 0.2, so 0.06. Now, who remembers, we only had one of these the other day, but I made a big deal about it. Who remembers when we have a situation that's this or this? What do? We add them, exactly. So the total probability of having a blue and a green in either order is 0.08. So as you read the problem, if it's this and this, it's times. If it's this or this, it's add. candy is chosen from each bag. What's the probability that neither will be red? Neither will be red. So what's the probability of not red from Maggie? 0.8. And the probability of not red from Elizabeth? So 0.8 times 0.7, because I want not red and not red. So 0.56. Watch your decimal points. If you are multiplying in your head, and that's absolutely fine, just be careful with your decimal places. Okay? All right, next section. Consider being dealt a 5-card hand from a standard deck of cards. Now, in order to do these problems, there is just some basic information you need to know about a deck of cards, a regular deck of cards. Okay? So, do you know how many cards are in a regular deck of cards, Jacob? 52. So, if you don't know this, you got spring break, look at a deck of cards and start getting familiar. You don't have to become a card shark. You don't have to become an expert card player. You just need to know about a deck of cards. The deck of cards, 52 of them, are divided up into 4 what we call suits. You know what I'm talking about? What are the suits in a deck of cards?
Ace.
No. The suits.
Diamonds. Hearts.
Diamonds. We have diamonds.
Spades.
We have spades.
Clubs.
We have clubs. We have hearts. And the diamonds and the hearts are red, and the spades and the clubs are black. So since there are 52 cards altogether, there's 13 of each suit, right? And then that means there's 26 reds and 26 blacks. Now the pictures on the card, so let's consider just the 13 diamonds. The 13 diamonds, you have a card that has just one diamond on it, that's called the ace of diamonds. And then you have a 2 and a 3 all the way up to 10, right? And then you have what are called face cards. They have like people with faces on them, and they are jacks and queens and kings, okay? So there's a queen of diamonds, a queen of hearts, a queen of spades, and a queen of clubs, and an ace of each, and 2 of each, and so on and so on and so on, okay? So if you don't already have that, that's all you need to know, that right there. If you already know that, great. If you don't know that, then you need to get comfortable with it, all right? Because we're not going to be able to answer the questions without that knowledge. All right, letter A. How many 5-card hands are possible? So we've got 52 cards here, and I'm going to deal out 5 cards to Kamari. How many different hands could I deal to him? Okay, any thoughts on that? It's a huge number.
Isn't that like the 52, 54, 50?
Okay, now, okay, so what he's thinking, that's good, you're thinking, it's not quite right, and here's why, but I like what you're thinking. He says, I'm dealing 5 cards. The first card I give him, there's 52 to choose from, and then there's 51, and then there's 50, and so on. That makes perfectly good sense. But here's what I want you to think about. When I am giving him a 5-card hand, and again, we're not playing any weird game. I am not a card player, okay? So I'm not into all those weird things. When I deal him a hand of cards, I'm gonna give him 5 cards. Does the order I deal him the cards matter? No. What matters is, those are the 5 he ends up in his hand. So, Brennan, this puts order into the problem, and I don't want that. This would be 52 P5, and that's wrong. That's what this says. I want 52 C5. because I'm going to pick 5 out of the pile of 52, and I don't care what order they're in. Okay, so go ahead and type that in. That is a big number. That's a big number.
215.
What is it?
989. Sorry.
25.
259. Oh my gosh, okay. 2598960.
98960. Okay, let's put some commas in there. How many hands are possible? Total hands possible in the deck are about 2.5 million. It's a lot. Don't bet your allowance on a particular hand, because you're probably not going to get it. What's the probability of being dealt a hand with all diamonds? Now, this is a probability question. It's a 5-card hand. The denominator is 52C5. That is the total number of 5-card hands. Remember, probability is what you want over the total. Question B is a probability question. So the denominator is going to be the total number of hands, which is that huge number we just came up with. You can write that down here if you want. I'm going to go like this. Okay? Now what goes in the top? In the top goes what I want, which are hands that have all diamonds. Okay, how many diamonds are there in the deck? 13. How many of those am I picking? It's 5-card hand. How many am I picking? 5. So my numerator is 13C5 because my numerator is what I want, and I want diamonds. So here are the 13 diamonds. I'm going to reach in and grab 5. That's my numerator. Okay? Now, I gave Kendrick my calculator, so I can't type this in, but I want you to. I want you to type 13C5. You know how to do that. And then just hit divided by. You don't need any parentheses or anything. 13C5 divided by 52C5. This is a probability, so it's going to come out as a decimal, and it might be a pretty small decimal, actually. You got an error. Okay. 13 there. 5. Okay, now what you need to do is hit enter or arrow. Okay, because you've got it. And then hit divided by.
Oh.
And then 52. Because see, when you hit that 5, see how it stays down low?
Oh.
If you hit this, it'll pull it back up where you need it to be. The answer comes out to be 4.952 times 10 to the negative 4th. Remember, we talked about this before. When that E comes in, that means you've gone into scientific notation. So the probability of being dealt all diamonds is 0.000495. Not a very good chance of being dealt all diamonds. How about all face cards? Well, it's still a 5-card hand. So your denominator is still 52C5. Every 5-card hand, if you're doing a probability, every 5-card hand problem, that's going to be the denominator. If it's a 6-card hand, the denominator will be 52C6. Every card problem you do, if it's a probability, your denominator is 52C, however many cards you're getting. And that's your denominator. Now, what's your numerator? That's going to change every time, depending on what you want. Well, what do we want this time? all face cards. So you gotta stop and figure out how many face cards are in the deck. Well, what did we say the face cards were? Jack, Queen, King. But we have, so there's 3 different kinds of face cards, but there's one of each in every suit. You know, diamonds, clubs, hearts, spades. So how many face cards are there? 12. So 12C5 is your numerator. There are 12 face cards, and you want to pick 5 of them. So that's going to be an even smaller number. All right, see if you can type that one in. Tell me what you get. It'll come out in scientific notation too. What is it?
3.047 times 10 to the -4.
So that, remember, scientific notation, we put 0.003047. So it's even a smaller number than you got here. You can leave them in scientific notation, so there's nothing wrong with that answer right there. Now, if you write 3.047 and don't write this, then you're wrong. Probabilities can't be 3, right? You need this part to make it right. Okay, all red. What's the probability of all red? Well, our denominator is still 52C5. Because it's a 5-card hand. 26C5. Now kids, please don't think you can just cancel stuff. You can't. You have to type this in. This is not going to be a very big number either. It's going to be bigger than these, but it's not going to be the big number like you would think. What did you get when you did 26C5 over 52C5? .02253. So that's a lot bigger number. That's actually about a 2% probability.
It's, sorry, I read it wrong. It's 253, just no extra 2.
Oh, okay, so you probably read it right. I just said it wrong. So .0253. So you have about, that's a decimal. So percentage-wise, that's about a 2.5% chance of getting all red cards. Would it be the same for all black? Yeah, because there's 26 blacks too, right? So it would be set up exactly the same. All right, what's the probability of being dealt, oh, this is gonna be tight, 3 jacks and 2 kings? Well, first of all, the denominator will be the same. It is still a 52-card hand, so that's your denominator. But I want 3 jacks and 2 kings. What does that and tell me? I'm going to be doing a multiply there. Don't make this hard. This is so easy. How many jacks are in the deck? 4. How many of them do you want? 3. So this is simply 4C3. With cards, we're always going to be using C's, so don't be worried about that. All right, there's very specialized problems where we use P's. So it's almost always a C. So there's 4 jacks. I want 3 of them. Done. All right. Kings. How many kings are in the deck? 4. How many do I want? 2. So that's 4C2. Now, you can type all this in. You don't need any parentheses. You don't need anything fancy. Just type 4C2 C3, you know how to put that in, times 4C2 divided by 52C5. Alright, so let's type that in and see if we can all come up with the right answer. Huh? What? Right there, that's what you're putting on. Alright, Caden, what'd you get? Here, let me just see it. This is gonna be really tiny. This is our smallest one yet. He got 9.234 times 10 to the negative 6. Anybody match that? Cindy? Good. Jacob, good. Kendrick, are you just typing buttons or are you actually typing this in? Okay. That is a really tiny probability, 0.00009. I mean, it's small. Again, don't bet your allowance. What is the probability of being dealt a hand with no face cards? Denominator, 52C5. The denominator is not going to change unless I do what? What's the only thing that's going to change that denominator, Jacob? Change how many hands I'm, or how many cards I'm picking. As long as I'm picking 5, the denominator is 52C5 from a standard deck. Alright, so now what's my numerator? My numerator is no face cards. So think about the deck. Here's all 52. I'm going to sort out all the face cards into one pile and everything else in another pile. How many face cards did we say there were? 12. So if there's 12 cards that are face cards, then how many are not face cards? 40. I want all not face cards. So what's my numerator? 40C5. Right? Aren't there 40 cards that aren't face cards? And I am choosing 5. So my numerator is 40C5. Alright, go ahead and type that in. That's an easier one. And that will be a bigger number. It's still not going to be big, but it will be a bigger number. 0.2532. So that's about a 25% chance. So not huge probability, but it's certainly better than the other ones we've done. Okay. What's the probability of being dealt a 5-card hand and having all of the aces? This problem is a little bit tricky. I want you to remember, how many cards are we dealing? 5. How many aces are there? 4. So what's happening in this problem is, I want to get 4 aces, but don't I have to get one other card also if I'm going to have a 5-card hand? And that other card isn't mentioned in the problem. You just need to figure that out. There's a 5-card hand. You want to get all the aces, but you still need another card. Okay? So, how many aces are there in the deck? How many am I getting? 4. So 4C4, there's my aces. There's 4 of them, I want all 4. And how many other cards are in the deck? That aren't aces, I mean, other things. 48. And how many of those do I want? 1. So this is how many there are to pick from, and this is how many I am picking. So there are 48 cards that aren't aces. How did Hugh know that? How many cards are there altogether? 52. How many of them were aces? 4. So how many aren't aces? 48. All right, type that in. This is going to be maybe the smallest one yet. Oh, no, actually, I don't think it'll be the smallest one. What do you come up with? It's gonna be something small. It's gonna be in scientific notation for sure.
1.842
What is it?
1.8472 times 10 to the negative fifth.
It's pretty small. So again, think about, you can write this down. That, first of all, did anybody match it? Anybody else get that number? Yes, Jenny? Okay. So this is a very small number. You can write it this way, the way it says on the calculator. But think about what that is. That's 0.00018. That's a really tiny number. Which, anybody who's ever played cards knows that your chances of getting all 4 aces isn't very good. All right, what's the probability of being dealt a 5-card hand having 2 tens, 2 jacks, 1 queen? 2 tens, 2 jacks, 1 queen. What's my denominator? 52C5. Probability means a fraction, kids. You're going to have a denominator in every probability question. Since it's a 5-card hand, my denominator is 52C5. All right, what's my numerator? I want 2 tens and 2 jacks and 1 queen. All right, any guesses about how we do 2 tens? First number, you're going to set up a C combination. First number is how many you got to pick from. How many tens are there to pick from? 4. How many are you actually picking? 4C2. 4C2. All right? Now, I want 2 jacks. How many jacks are there in the deck to pick from? 4. How many am I picking? 2. Another 4C2. Then I want a queen. How many queens are there in the deck? 4. How many am I picking? 1. 4C1. So 4C2 times 4C2 times 4C1. Everybody got it? All right, let's type it in and see what we can come up with as an answer. It'll be tiny. Times 10 to the negative
Fifth.
fifth. Anybody match that? 5.541 times 10 to the negative fifth. Ayrton, you type that in? Okay, so somebody else match that. Another very small number. What is the probability of being dealt a 5-card hand with no aces, no queens, no 5s? So first of all, 52C5 on the bottom. My top is no aces, no queens, no 5s. You can do this a couple of different ways. I like to just think about my deck. Here's my deck of cards. I don't want to have any aces in my hand. So I'm just going to pull the aces out and lay them over here to the side. How many aces are there? 4. So I'm pulling those 4 out and putting them away. I can't use those. Now, I also can't use the queens, so I'm gonna pull those out and put them over here. How many of those are there? 4? So now I've got 8 cards taken out. I don't want any 5s either, so I'm gonna pull those out. How many of those are there? How many 5s are there? 4? There's 4 of everything, right? So, how many cards have I pulled out of the deck? Because I do not want them. I do not want these cards. I pulled out 12. So how many are left for me to actually pick from? 40. So of those 40 cards, I want to pick 5. This is how I would do the problem. I would just peel out the cards I don't want right from the beginning. And I think we had this one before. We did this on another problem. This one's point, what is it? 0.025 something?
2.2532.
Oh, 0.2532? So that one, we had it, yeah, right here it was, yeah. Now, other people will say, okay, you don't want any aces. That's 4C0. Well, type that in. That makes sense to me. There's 4 aces I don't want in. But figure out, what is 4C0? What does that equal? Just 1. And so I don't waste my time writing that down because I'm going to be timesing, and timesing by 1 doesn't change anything. So if it helps you to clarify, say 4C0, I'm good with that, but you don't, and 4C0, and 4C0, and 40C5, that would be your numerator. If you literally put in, I don't want any aces, I don't want any queens, and I don't want any 5s. But I need 5 cards out of the rest. All these are 1s, so I don't write them down, but you can if you want. Okay? All right, so real quick, I'm going to give you a problem to do, and I want you to type it in and give me a decimal, everybody. All right, so we're going to have a 4-card hand. This is a 4-card hand. What's the probability of 2 red and 2 black? All right, so do that for me. Set that up and solve that problem. Okay, what's your setup look like? Let's make sure you got the right setup. What's your denominator? Your denominator is your total. 52C4. Perfect. That's your denominator. All right, your numerator is what you want. 2 red and 2 black. So we're gonna have a multiplication, right? Okay, how do I get 2 reds? How many reds are there? 26. How many do I want? 2. That's 26C2. And, okay, how many blacks are there? 26. How many do I want? 2. There's your problem. Has anybody typed that in, Brennan? 0.3902. Wow, that's a 39% chance of having that happen, if that's the right answer. Did anybody else get that? Perfect. Okay, now, got good news and bad news. Good news is, the problem, 9-3 is a big section, so the homework is split into 2. There's 2 9-3 homeworks, and you are now ready to do the first one. So 9-3, number 1, will be below 2C. non-free number 1 will be due on Tuesday. All right, have a great spring break. Please be safe and smart, people. Be safe and smart.